Hey everyone, this is Lucas Wilkerson, the math coach, and today we're going to be working through some problems through 3.1 through 3.5 to 3.7. Question number 1 of 3.5 says find the domain of the rational function. To do that, we want to look at the denominator and we want to set it equal to 0. So setting this equal to 0, we see we can take an x out of both, and we can solve each of these pieces for x. Here x equals 0, and here x equals 16. So these would be the answers that we exclude from the domain. I'm sorry if I have the sniffles that comes across the mic, a little bit of allergies. So the domain, you could write like this. So for x, all x values that are not 0, and x that are not 16. For number 2, it says use the graph of the rational function to show the complete statement. So when you look at where the asymptotes are, looks like we have one at -2. We have one at +2. So now looking at this, it wants to know at -2, what's going on the left side. That's what that negative means. So the negative side of the -2 asymptote. And if we observe, we see it's going towards -infinity because the graph's going down. Now if we look at the positive side of -2, so that's looking at like this, we see that it's actually going up. So we're going to have positive infinity. Now this is +2 right here, but we want to look at the negative side. So doing that, we have this piece. We're going to see that it's positive infinity. Do the same thing right here. +2, positive side is going to -infinity. So that's how you do that. Just remember, when you look at these, this negative means to the left, and this positive means to the right. So looking at number 3, we have one that I would say is a little more complex. And we'll see for both of these as they continue. So this is at -infinity. See, it keeps going this direction, and it keeps getting closer to that asymptote of 0, just right along the x-axis. And when the infinity is positive, it's doing the same thing. It's coming down, but it continues to get closer to the x-axis, which would have a y of 0. So for number 4, it says find the vertical asymptotes, if any, of the graph of the rational function. So to find vertical asymptotes, first we're going to need to check if there's any holes in this equation. So we start by simplifying out the denominator. This numerator stay the same, but x squared minus 1 we can simplify to x plus 1, x minus 1, which is the same thing, and we could cancel these two out, which leaves us with f of x minus 1. And then just like for problem number 1, we'll set the denominator equal to 0. And when you do that, you find x is equal to 1. And there, we would have our vertical asymptote. All right, here for number 5, 6, and 7, it says find the horizontal asymptote, if any, of the graph of the rational function. And there's a little trick to this. So looking at number 5, when our exponents are the same, our leading exponents, they're both squared, we really don't have to do nearly as much of the work. We can just take their constants and solve that. So we'd say y is equal to the 25 over 5, which if you punch that in your calculator, y equals 5. And that's how you find the vertical asymptote when the leading coefficients, when the leading degrees are the same. You look at the coefficients. Then for number 6, you see the bottom leading degree is more than the one on top. So when bottom larger, we just say y equals 0. You don't have to do any work. You can just see that. Then for number 7, our top degree is larger. So when top bigger, or I'll just say larger to use the same language. When top larger, we have no asymptote. Now look at the next set of questions from 3.6. Looking at question 2, it says solve the polynomial inequality and graph the solution set on the number line. Express the solution set in interval notation. So to do that, we want to start by getting the x value, well, we want to start by getting everything on one side. So we're going to add 12 to both sides. And then we're going to ask what multiplies to positive 12 and adds to negative 7. And we'll see we have x minus 3, x minus 4, which is greater than or equal to 0. Solving these, we get x equals 3, x equals 4. And then when we go to graph these over here, we're going to have, so when we go to graph these, I think the easiest way to think about this is draw a line like this. And 3 is less than 4, so just plot it like this. And then take these two numbers, your 3 and 4, and plug in numbers to the left and the right of them. So for example, at this 3, if I was to plug in 2, or here's an easier one, I'll plug in x equals 0. And if I plug that in, I'll get a positive number. So it's going to be positive on that side. And here I'll plug in 3.5, and I'll get a negative on this side. And then if I plug in a 5, which is greater than 4, it's positive on this side. So that kind of allows us to know around these numbers, it's going to be looking like this. Or an easier way to describe it, I'll just draw it. Here's 3, here's 4. And our graph is increasing in these ways. I just found that out by plugging in numbers around those values into the original equation. So looking at number 3, we'll repeat these steps. Easiest way to think about this is divide it into two pieces. So I'll take an x squared out. And then I'll take a negative 1 out. And now you see these two pieces match. So we combine those. Then we just take the x squared minus the 1, put together like that. These are all just greater than 0. Then this x squared minus 1, we can actually split into x minus 1, x plus 1. Now we can just see x is negative 6, x is 1, x is negative 1. It will test some values around them again. Negative 6 here, negative 1 here, 1 here. Let's plug in x at negative 7 into our original equation. And we'll see we get a negative value. Then we plug in negative 2, we get a positive value. Between negative 1 and 1 would be 0. Get a negative value. At 2, we get a positive value. So the spots where it's positive would be, let's just sort of decide where these points are. Make this negative 1, make this 1. And we don't have the include sign, so instead of these brackets up here, we'll just use parentheses. So at the negative 6, it's positive on the inside piece, so it goes like this. and it stops at -1. And then at 1, it goes positive in the right direction. So put this parentheses, and it increases going on forever. Then if you need to write that in the interval notation form, it's like -6 to -1, u1 infinity. Looking at section 3.7, it says solve the problem if y varies directly as the square root of x. Let me say that again. If y varies directly as the square root of x and y is equal to 4, when x is 25, find y when x equals 64. Oh, that's a mouthful. So key here is when it says varies directly. Your professor, your teacher should have given you notes that look like this. So when it says direct, we have y equals kx. When it says joint, we have y equals kxz. And when you have inverse, you have k over x. So since ours is directly in the square root, that means for the first step, we're going to have y equals k square root of x. And we're given that when y is 4, x is 25, so we can plug this in, and we can solve for this k. In a second, you'll see why that's important. So we get k is 4/5. So for the second part, we need to find y when x is 64. This time, we actually know what our k is. So now we can plug in 64 for the x. And when you solve, you'll get 32 over 5. So really the only trick here is remembering this, and the rest is just basic algebra. For 3, when x varies inversely as y squared, find x equals 6 when y equals 10, and then find x when y equals 5. So for our first step, we're going to have when it joins inversely, it's going to look like this. X was the first, so it's x equals, and then inversely is k over the y squared. So when x is 6, y was 10. So we have 10 squared. And if you solve this, you're going to get that k is 600. So we can go to the second step. And we're going to be looking at x over 600y. And we're given that y is 5. Solve this, and you'll see x is 24. Moving on to the final problem, number 6, a big hefty word problem. It says the pressure of gas varies jointly as the amount of gas. Okay, so the pressure varies jointly as the amount of gas. And the temperature in the temperature inversely is the volume of the gas. Okay, so that's another piece. If the pressure is 1,395 kilopascals, when the number of moles is 7, the temperature is 310 Kelvin, and the volume is 840 cc. Find the pressure when the number of moles is 5, the temperature is 330 Kelvin, and the volume is 600 cc's. So that's a lot, but first things first, if we set up the equation, we'll know where to plug these things into. So the pressure of gas varies jointly to the amount of gas, and the temperature is the inverse of the volume of gas. So the pressure is what we're solving for. We know the volume's inversely, so the volume's in the denominator. And we see jointly the amount of gas and the temperature. So it means we're going to have K times gas times temperature. So our equation looks something like this. And then we just need to plug in the information they gave us. So the pressure is this number, which is equal to the number of moles is 7. It's going to be for our gas value. And then the temperature was 310. And the volume was 840 cc. So now that we have this set up, all you have to do is punch this on your calculator, solve it around, and you solve that K is 540. Now that we've solved K, we can go back and plug this in for a second time. So let's write this. We know K is 540. And now we need to find the pressure when the number of moles is 5. So that means we have 540 times 5. The temperature is 330. And the volume is 600. That's how you set up for the second time. And when you solve, you'll get this many kilopascals.